Good. Thanks. Good. So let's, we looked at permissionless blockchains in the first part, and now, let's look at the space which I believe will be more close, or it will be closer to the expertise that the audience has, and to us as database researchers. So if you think of permissioned blockchains, these are basically systems where we have identities. So if you recall from the beginning where I was saying that we have public key cryptography, where the existence of key pairs doesn't necessarily mean these are tied to some identities. In permission blockchains, we by definition have nodes have identities, and these identities can map to natural persons or companies or legal entities. In some sense, what is important to note here is that the in a permission blockchain, the members or the parties interacting share some common goal. That's why they enter into these systems together, which is of course not to say that they don't want to protect against malicious behavior, but overall, they all agree on some shared goal. So that's why you have a supply chain management system. The shared goal is that you're exchanging information and tracking these products throughout the supply chain, which is beneficial to everyone involved, right? It is important to note that in permission blockchains, typically the use cases, so this is now not necessarily about something fundamental about permission blockchains, but more about the use cases and to put you in the right mindset. So typically it's not dealing with fully virtual assets. So and there's legal frameworks around parties doing business together. So you can imagine if two companies are exchanging information on the blockchain, they will already have some kind of legal frameworks in place otherwise. So in some sense, whereas in the permissionless space, the main goal is to be able to overcome failures and continue operating under highly malicious activity as well. Here perhaps you can relax this, and sometimes it's enough to detect that there's problems, and we don't have to transparently solve them because there will be other mechanisms. Like if, for instance, a supply chain suddenly claims that a washing machine was delivered twice in a permissioned setup, I can go and verify this offline and see where the washing machine is, right? It will not be physically in two places at the same time. And in terms of deployment or provisioning or system, the back end, because these systems are run by, as I said, organizations or individuals who want to do business together, there's in general more control or at least understanding on the placement of the nodes and the different code that they run. So there's a shared common goal. It makes sense that everybody is, for instance, using some reasonably powerful hardware. Now, if we look at the permission space, because we have identities and we know who the participants of the consensus are, we can basically rely on traditional consensus algorithms. Most importantly, the Byzantine fault-tolerant consensus algorithms, which, as you maybe recall from, or even if you're not an expert in this space, they are based on majority and typically take several rounds of communication across nodes. However, as a benefit and something that is, for us in the database where it is very natural, they offer transaction finality. So basically, once we have, voted and agreed on a transaction or on a block, it will not be reverted. There's no artificial rate limiting. So what I mean here is that, as we saw in the first part of the tutorial, in different systems for various reasons, you might want to either reduce the throughput of the system so that you can, for instance, perform gossip in the back reasonably well, or you want to save on other resources. Here, in principle, you can go as fast as your infrastructure allows you. Now, of course, with BFT consensus, there are some challenges in reaching consensus across a large number of nodes. So this is typically once you go into the hundreds or thousands, there can be challenges, but there's different solutions to this. And if you're interested at the end, we can circle back. So there's both kind of algorithmic changes or the way that you organize consensus, like with the delegation to basically reduce to reduce the number of nodes which actively have to take part. But it works for most, for most cases with the technology we have today. You can run a permission blockchain on several hundred nodes, and it will work. If if I look at it kind of at a high level, as I said, because we have identities, the nodes in the network know who the others are. This also means that there is some onboarding process, right? And you can actually take people out of the blockchain if they misbehave. So you can actually you can have mechanisms to, so to say, to punish people in the real world for what they do on the blockchain. And data itself is not public, right? But you have to remember that the data is visible to all members of the blockchain. So still, you have now, you have control on who can actually access this network or this blockchain. But within the members of the blockchain, data will be public. Now, there's again ways in which you can work around this, and you will see in the example in the exercises. There's one way in which you can do this, for instance. But this is up to the basically the implementation of the permission blockchains to deal with private data. And as I said, use cases are like companies sharing data sets, e-governance, notary, supply chain management, and so on. So this is something where I would say more the database thinking comes into place. So once we talk about permission blockchains, that's where programming the blockchain becomes also more interesting, so to say. And smart contracts, as you have probably heard, are the way to program these blockchains to add user-defined functionality on top. And you can think of them as stored procedures, or in some case, like triggers that run on the blockchain. Now, some blockchains will allow users to add custom arbitrary smart contracts. Others will have a set of operations baked in. So for instance, in a Bitcoin, there's no really notion of the smart contracts is designed together with the system, and it's not something that the clients are able to influence. In a permissioned blockchain like Hyperledger Fabric, it is up to the clients to define their own stored procedures, their own smart contracts, and load them. Of course, these contracts can take different levels of complexity. So they can be very simple, like transfer of tokens or escrow accounts. But you can also write arbitrary programs. And this is where it becomes more interesting for us as database people. So typically, these smart contracts are written in some domain-specific language, and they will operate on a key value type of abstraction on top of the blockchain. So you will operate on a materialized view of the state. When I say arbitrary programs, there's a small caveat there, is that these programs have to be deterministic, because if you think about it in a very high level way, if you run this program at any participant in the network, it has to result in the same outcome, right? It cannot deviate. Otherwise, the state that we perceive in the blockchain would diverge across nodes. So that's why typically these programs are written in DSLs, domain-specific languages, which remove the sources of undeterminism that otherwise would be present in a general purpose programming language. And smart contracts, you can think of them, as I said, as either baked into the system, like hard coded into the actual source code of the blockchain, or you could store them as well on the ledger. And you can say, if you think of a stored procedure, you could say invoke a transaction which is to be found on block number 10 at position whatever 3 inside this block. There's a piece of code, and run it for me. There's if you can store them on the ledger, this of course gives more programmability. So in permission blockchains, typically this is the case. You can add your own smart contracts. Interestingly, even in the permissionless space, for instance, with Tezos, the system allows so-called updates or programmability of the Tezos code itself. By agreeing running consensus, you can update, so to say, the system as it goes. So smart contracts are not limited to permissioned blockchain. They are also in permissionless, and the way they the more or less flexibility is also exists in both places. Okay, so now if we look at how a permissioned blockchain system looks like, and this is a cartoon version of Hyperledger Fabric, but this is basically true for any other permissioned blockchain, it looks something like this. So we have logical roles. And again, these logical roles might actually be co-located on the same physical machine. So there's a, you have some client who will invoke a smart contract, and these smart contracts will be executed on executor nodes. These executor nodes will submit transactions for ordering. So ordering is basically to find a global total order of the transactions, or to create the blocks, right, in the blockchain, which is done by the consensus nodes. And once these are assembled, these blocks are sent back to the executor nodes, which then can use these to update their state and whatnot. As you can see, there's also an external kind of cloud here, which is a trusted party or consortium of the nodes themselves, which are used to authenticate and configure onboard newly joined nodes, or to remove ones which are faulty or misbehaving. As you can see, there is, in these systems, typically you would think of the nodes involved in consensus in the order of tens, and then the nodes which are executing smart contracts in the order of hundreds. Again, these numbers might differ, and there could be larger or smaller systems, but this is just to give you a feeling for the size that most of these systems in practice are being considered. Inside the executor nodes, you can have two types of execution models. And this is where things get actually very similar to databases. So we can have something like active replication, where the idea is that a client submits transactions to be executed. So think of transactions as I said, like stored procedure invocations. And these transactions are submitted. They are being ordered into a block, or just globally total ordered. And then they are executed at every single executor node in order. And the changes are committed to the local ledger. So this is like, in the database term, you can think of this as active replication, where every single node will execute the same operations in the same order. Now, here, one of the drawbacks is that the complexity of the smart contract that you wrote will determine the execution rate, because even though you could, in principle, parallelize some of these executions, you have to be careful, as I said, not to introduce undeterminism. And this typically means that they are executing in serial. So if your smart contract would, for instance, do some very, very complicated operations, then every other smart contract behind it, so to say, waiting to be executed, will be delayed. So this is the order execute model is used, for instance, in Ethereum, which can be also used as a permission system, and it uses this approach. Hyperledger Fabric, which is a permission blockchain designed for more enterprise use cases, adopts something which looks more like passive replication in databases, where a subset of the peers will basically execute the transactions. They execute the client transactions. They will generate a list of, you can think of them as read-write operations that these transactions perform on the data. If all these, all the nodes that endorse this transaction have the same read-write set, then this transaction is considered correct or orderable. It will be assigned an order in the log, and then in the validation step, the read-write sets will be applied onto the ledger. So this is, if you think of passive replication here, basically I'm only executing the smart contract, really executing it on a subset of the nodes, and then all other nodes record the outcome of these transactions in the ledger. So what happens here is that this kind of model decouples the cost of updating the ledger and doing consensus from the cost of running the smart contracts. So here I can run a wide range of applications, even those which are more expensive to do, because the cost I'm incurring on all the nodes is only that of recording the read-write sets in the ledger. So if you think of here, if you think of something like a banking example, where two banks, that you have a consortium of 10 banks, and two of them want to do some kind of shared computation, right, with a smart contract. In the order execute model, everybody has to execute that smart contract, even if the transaction doesn't really is of interest to them. In the execute order validate model, you can pick a subset of the nodes. So for instance, those who are actually involved with the computation, and then use the other ones to simply validate the resulting read-write set that it's compatible with the state of the ledger. And this is really where the main drawback of the execute order validate approach comes, is that because the execution between executing a transaction, so simulating a transaction and recording its outcome into the ledger, you have several steps, right? Several distributed steps being performed. What you work on is a materialized view of the ledger at the time of simulation. By the time you're trying to commit a transaction, this actually might change. I'll show that in a slide in a second. So the state DB, as there was a question previously in the previous part, is you can think of it as an index or materialized view on the data, where if I have a series of operations in the blockchain, I can update this key value store with basically the keys that are in use and their most up-to-date value. So I can, even though I have this long list of blocks being added and updated, I can see its most up-to-date overview in the state DB. So this is typically in Hyperledger Fabric and other systems, a separate key value store that runs on top of the blockchain inside the nodes. Maybe this is something that we don't have the time to go into, but there's a lot of interesting discussions on whether to use, for instance, persistence, or whether use like a full-blown key value store here, which can also make its checkpoints and persist itself to make recovery cheaper, so that you don't need to go back and reconstruct the state whenever there's a fault. Other systems might actually, prefer to have a very thin in-memory key value store type of representation, and then whenever there's faults and nodes have to restart, they read the blockchain from the beginning. So if we look inside an execute order validate node, and this is, I think, what really, as I said, resembles more what we think of in databases. What you have is kind of two different paths for blocks or transactions to come in. So one is the request to simulate and endorse a transaction, which happens, in parallel to other things, and it relies on the state DB. And then you have, once blocks have been ordered, you are doing some validation. So it actually verified that, signatures are correct and the data itself, everything checks out. And then these changes are recording into the ledger. And as I mentioned, the problem is that in Fabric and similar execute order validate systems, you are endorsing smart contracts on this materialized view, but then it will take perhaps hundreds of milliseconds until you get the ordering done and you record the results of these transactions in the ledger. So you can imagine if you have something like a read, modify, write pattern, then you can have transactions that fail because by the time they are recorded in the ledger state itself has changed, and this read-write set will not match, will not be compatible with the state of the ledger. So what most systems do is basically retry transactions. So this is not possible. I just want to highlight in the order execute model, the transactions are first ordered and then everybody executes them in the same order. So you can have a transaction. You can have, there's no way in which a transaction can fail due to another transaction changing the data, before them. So what happens, of course, in Fabric and in other similar systems, you can get around some of these problems of stale data by adopting a suitable programming model or change the way these read-write sets are expressed. So if you can, for instance, instead of saying a equals 1, if you use increment a by 1, then of course that's an operation that can be applied even if the underlying ledger changed, right? Okay, but overall in the systems, and this is something that I myself been exploring for a little while, is that if you can reduce the latency, it takes between validation and endorsement and validation / write into the ledger, you can actually reduce the chance of transactions failing. Okay, so to recap this space, what I think is important to remember from permission blockchains is that here all nodes have identities, and data is, but data is still public within the members of the blockchain. So it's not public to the general public, but anything that you record in this blockchain will be readable by any current or future members. So you have to be careful. There's methods of, for instance, encrypting data or picking ways in which you can make this partially private. In many ways, I think a permission blockchain does resemble a distributed database, and many of the ideas that we are, but that we have in databases about how the system should run apply, and many of the optimizations could apply. And in terms of execution model, I just want to highlight here that going the execute order validate way, even though it has some of these drawbacks of potentially stale data, it allows a more flexible way of supporting powerful smart contracts and keeping some kind of privacy within these blockchains. Again, I think what is important to stress is in comparison to Bitcoin, where really I don't know who else is on the network, and if they misbehave, I have no legal recourse to them. In permission blockchains, typically you can assume that these are not fully virtual, and there will be some frameworks around them. So this is, the question in the previous part was about banking. So if you think of banking transactions, I would make the case that they fall more within the permission space than in the permissionless space, because you will have some form of identity, right? The bank will know that it's you or someone else making transactions. And for this reason, you can rely on operations which resemble more databases than proof of work and proof of stake, right? Having a system which is permissioned doesn't mean that it cannot be open to the public. So there's, for instance, proposals from Spain where I've been working before, where I know that they're working on a kind of permission blockchain where the condition to entry is having basically a tax number, right? So any business who has registers with the Spanish tax agency can enter the blockchain. So it's public in the sense that in principle anybody can access this blockchain, but you need identities to do so. So you cannot do it anonymously. Okay, as a takeaway, before I very quickly show you the exercises, what I think is important to remember is that permissionless and permission blockchains do share a common data structure. So this is where they are very similar in the underlying data structure. But this is also, I think, calling them the same, calling them both blockchains is in some sense making a disservice, because if you look at other aspects like the consensus model, they are fundamentally different. So proof of work and proof of stake is fundamentally different in the way it operates, but also in the way it looks at the world when you compare it to BFT consensus. I think, and this is my opinion, so you might disagree, but I feel that in the permissionless space, the current challenges are not necessarily technical. So I think the most of the science is there to make the systems work well. It's more about economic incentives, game theory, and so on. Public education that one has to work in. Whereas on the permission side, I think indeed we are facing many data management problems and processing challenges. Like one example is if you think of multiple banks entering into shared computation. How do you unify schemas across banks? How do you connect this blockchain system to existing databases in the banks in a way that reduces overhead and impedance mismatch between what's going on in the blockchain and in the database? So if you want to perform analytics on some of these things, how do I efficiently take data out and run it through analytics and perhaps even feed the results back into the transaction? So you can see that these kind of questions feel a lot more about database know-how and a lot less about economic incentives. And then I think what is important for performance tuning is to consider that whereas the permissionless systems typically would be designed to run in a widely distributed setting with low bandwidth between machines, if we look in the permission ones, in many use cases, we have much more controlled environments. So this is not to say that you couldn't run it in a geo-distributed setting. You could absolutely do it. But in many use cases, if all the parties reside within the same country, it perhaps doesn't make sense to assume geo-distribution beyond the confines of that country. So this actually opens up optimizations for dealing with faster networks or more powerful machines, because they might be all sitting in the same cloud, or in a few cloud providers connected with high bandwidth links. Okay, so any questions here before I just give you an idea of the exercises? If not, then I'll just quickly do this so that you have an idea for. So you should see my a VirtualBox image. Is that correct?
Yes, I can see it.
Okay. So what I've set up for you is basically a virtual machine image that you can download, and it has two applications in it. And these applications, so one of them, actually, maybe I have some slides. Maybe we should go like that. So these applications, one is a supply chain management example, which resembles more the private permissioned setup, and then Gain Sierra is something based on tokens, which is more like a public permissions application. And through these exercises, which of course we don't have the time to cover here, but you can do it at your own pace at home, you will see how the smart contracts are defined, how you can put an interface on it, how things look like. But as just to give you an idea of the supply chain management use case, what we wanted to set up is the following question. You might have some farmers producing produce and then shipping it to your local grocery store in a very climate conscious way, with very little CO2 emissions. Or you could have others which are doing a very lousy job, or bringing things in from another continent, and you as a consumer, for instance, have a very hard way of telling these two. So the supply chain management example basically has this entity. So it has farmers, shippers, and distributors, and they are under the obligation of disclosing to the blockchain what is the CO2 emission footprint of either producing an item or sending it to a distributor. And then we have something like, you can think of it as a trusted entity, which is the evaluator. For instance, it's a government agency, then looks at the blockchain and based on the history of an item, gives an item an evaluation and then records this evaluation on the blockchain. So you can think of this as now the consumer can basically in the supermarket, scan the produce. I'm making this up, but like you can scan the produce and then you can get this evaluation from the blockchain. Of course, you as a consumer, you are not, you shouldn't have access to the actual cost of or the actual footprint of these items. So what we have done is, in this example, we have encrypted the footprints, the CO2 footprints that you're recording on the blockchain. So you will see in the examples, I really don't want to go into those details, but you will see how encryption works, and then using public key cryptography, only the evaluator can decrypt this footprint. So both the farmers and the shippers put the footprints encrypted with the public key of the evaluator, and then the evaluator can look at all these footprints in a plain text way and generate the evaluation. So the way what you will see is basically an end-to-end example where we have provided for you the chain code. So the chain code is basically a smart contract for Hyperledger Fabric, exposing through some command line interface, so you can play with it on the command line as well. But we also created a small web application on top, written in Python, that can call these functions and then put it on a, well, not very beautiful, but let's say very basic way on the web. So this is what you'll see. So just to give you an idea, so you will download this repositories, and what following the steps, you can start up the application itself, and you will have an interface like this, where, for instance, I can add an item produced by a farmer, and this, I don't know, has a footprint of 30 tons of CO2, and I can ship it to some shipper. Now you will see that the system is a little bit slow, because what happens is, of course, you're inside the virtual machine, and Fabric itself, if you recall the high-level description, it will run several executor nodes and several consensus nodes. So even if you're running on a single machine, it will create multiple Docker images running in parallel. So I recommend that you don't do this on your laptop like I'm doing it now, but do it on your workstation so that you're not overwhelming the system. So now, for instance, this is recorded in the blockchain. I have some public information that this produce called watermelon was shipped to shipper 1 with some encrypted footprint. So now if I go to the interface of shipper 1, this will show that there's a pending item, which can be sent further, for instance, to maybe another shipper, right? So this is maybe produce that goes around the world, very inefficient. So now if I go to shipper 0, I can see the same information, and I can send it to a distributor. And then to finish the example, once a produce arrives at the distributor, the evaluator will see it as being available for evaluation. And this is kind of the trusted step, where inside the evaluator will use its private key to decrypt all the steps of this watermelon and make a verdict. Now, in this case, it will be not very good. It will be bad for the environment, so the consumer can see that this is negatively evaluated. So this is the example we provide to you, and what you'll have to do is there's steps. Let me just see. So here there's a repository. You can download this, and then there will be exercises inside, like adding different features to it. What I want to highlight is to make the connection with the smart contracts that I explained before with Hyperledger Fabric. So basically, the state of the word, or the state of the blockchain, is in Hyperledger Fabric represented as key value pairs, and the values can, of course, be it's a nested data structure, so you can basically put anything you want in these values. And then you have two types of smart contracts: one which alters the state of the word, so you can basically modify the blockchain; then others which query it. Regardless whether it's just a query operation which doesn't change the state, this will still go through the consensus, and it will be basically handled the same way, except that it doesn't change the state of the database. And as you will see, all these smart contracts can receive parameters. So I made the comparison to store procedures. You will use different, in the exercises, you will define even your own transactions with your own parameters to make things happen. Yeah, so basically we are you will see that the way you're mapping to this key value store is nothing, is very much similar to how you would do it in the database. So you can set up tables. Basically, you can use the keys as primary keys. You can do it in a very nice normalized way, or you can also denormalize and then have nested data structures. Let me just see what else, because we, time-wise, I want to make sure we have time for questions. Okay, so this will be one example that you will do, and you will see there's guided steps. And these slides are all on my webpage. Please take a look. So the other application that you will see is a simplified version of a startup that actually got conceived by some ex-colleagues of mine from ETH, which I think is a very nice initiative about using blockchain to try and fight deforestation. And our copy, we did this when we were in Spain. So this is centered around Madrid. And the idea is that this is a token-based system where users who register with the system will stake some of their money around different regions around the city, saying that I I will personally, or I bet, or I will personally take steps to make sure that this part of the nature around the city will not be deforested by whatever next month or next year. And then the idea here is that if you look at the entities, so you will see the example, you have users who can basically pick a tile and say, I'm putting money or investing in the idea that this part will not be deforested. And then if if you're right, then you get money from the other, let's say, losing tiles. And if you're wrong, then you lose your money. Now, the incentive here, of course, in Game Forest is that the users are, for instance, local farmers who will use more green methods of farming. And then there's an evaluator, which we have in our example as well, who will determine which tiles are, let's say, doing well and which tiles are, being deforested. And this in Gain Sierra, in Gain Forest, is done by, taking satellite images in a weekly or monthly fashion, and then analyzing these images with machine learning and figuring out which tile is in a good shape or not. Of course, in this small example, it is all kind of a random coin flip, but it gives you an idea. So this is what you will see. It's a different type of application where instead of dealing more with like data management, well, more like items and shipments, it's about some state and then some bets, so to say, and user balance. So this is you will see if you go into the repository, there's a file with exercises. I don't know if this will open now or not, but there's a file with exercises, and then you have the solutions also actually done for you, so you can check them out. Okay, so where is this? Just to as a recap. So if you will have my slides, I guess. I assume, or the recording in the EDBT website, and this is the link for all the information. So if I don't know if I can go there. No. So if you go to this link, it will have a text describing how to download the virtual machine, how to check it out that it works correctly, how to get the exercises, and the link to the slides I just showed you very quickly. So you should be in good hands. Of course, if there's any questions or issues, feel free to email me throughout your adventures. Okay, so with that, I would we can either we can take a poll if you want for further discussion. So maybe I can put this up, or in the meantime, if you have any other questions, then maybe that's something to handle now. But maybe let's do this just for. Can you still see my screen? I assume so. So if you do, then please go to this site and just let's pick a feeling for for the remaining 10 minutes or so. If there's any specific aspect that you would find more interesting to discuss, you can also go not interested in, and then either you can ask me the questions or we wrap up sooner. That's but I think we should take the opportunity to discuss some more.
So just to let you know, that we just created now specific rooms for people to discuss their papers and also keynotes. So you can even after the session, make yourself available there, and people can join you. You just yeah. So these are indicated as discuss your paper, but it's also we will also probably open one specifically for keynotes.
I think that
and tutorials as well.
I think that's a good idea, especially with the virtual machine and stuff like this. I think that's maybe good to that people
anytime
can find
if you make yourself available, you can.
Okay, so I see that people are not voting, so that's
just give us a second.
That's also okay. I mean, we can also go for questions in a second, but let's just wait.
I have lost the link to the voting.
So it should be menti.com, and then you see up here. Oh,
it will help if you paste it in the chat. So
yeah,
that
I can
people
absolutely. Let me.
It.
Yes, let me do that. Just a second. So I just posted in the chat the instructions.
Yeah, Okay. So will this help you to?
So this is basically for me, it gives me a second so I can breathe.
Okay.
And we can pick maybe the last, the last quick topic we discussed before we wrap up for questions.
Okay.
Okay. So okay, this is like the the outcome is very varied. So I think so one topic, as I said, is between understanding how data is being represented in the blockchain and how this can have like repercussions on how you process it. And then I see the other is the proof of star consensus, which seems that people are interested in. So let me quickly just let me go start with this, and then we can talk for a second about UTXO. So in terms of we talked about proof of stake and proof of work. There's also other ways in which you can basically enforce that that there's no CBL attacks happening. So if you recall, for instance, in a system like Bitcoin, the main idea is that we want to give everybody an equal chance to speak, but we don't want to let bad guys to be able to create a lot of fake identities so that they can get a disproportionately larger chance of speaking. So there is interesting proposals like proof of personhood, which, for instance, is a way in which I can prove to a system that I'm a human, and by proving that I'm a human, I get basically an equal chance of voting. Which you can imagine is, again, this is now in the space which is not necessarily about like cryptographic primitives and theory, but more comes down to how they verify that the person is a person, right? There's other ways, like if you think of proof of work, which is a rate limiting type of setup, right? And makes you burn energy, right? So makes you pay more if you want to try and get more of a say. There's things like proof of elapsed time, which relies on enclaves. So for instance, SGX, to say I waited n minutes before I put a new suggestion for a block. And here the idea is that it's, if you want to subvert the system, you will have to buy a lot more processors. So you will still pay a cost, but you are not actually doing costly work. You're just waiting around until your turn comes, so to say. Of course, this, for instance, proof of elapsed time is somewhat controversial because it relies on SGX enclaves on Intel, basically on Intel being somehow a trusted entity in this system, right? So you can imagine that many people in the space who believe in really not having a central point of trust or see a problem with this. There's other ways which I think to me sound like more interesting, and definitely a space where like database researchers can have a say, is for instance proof of storage, where you can think of basically proving like we are sharing, I can prove to everybody else that I take my fair share of storing some information related to the blockchain, and then through this I get my let's say my ticket to vote, right? So then the cost of me creating fake identities is that I need to have more capacity to store data, because I need to store more. So it's still costly for a malicious actor to try and mount a 51% attack, but for humanity or for the members, it's somehow more useful because you're actually storing data, you're doing something useful for the system. In the proof of storage, or like proof of storage, this is coupled with zero knowledge proofs. So basically the point is that you want to show to people that you have stored data without actually disclosing what this data is. And this is where I think for database researchers, in case you're not following the multi-party computation / zero knowledge proof space in the theory side, I think there's many open questions there in terms of performance and optimization that can be interesting. Also, if you think of something like planetary file system, again, there's many ideas which I think the database people understand very well and could be useful in that space. So that's about proof of star. So there's, of course, you can come up with other types of proofs, and I think there's there was just a paper in EDBT, or there will be a paper tomorrow on proof of execution, which is somehow combining ideas of this execute order validate type of processing with some kind of proofs, so to say, that you can show that things were done in a correct way, and allows consensus to happen without actually having to do costly additional operations. Okay, so that was one thing which it looks like it's interesting. And then the other question is, so I talked about data representation and how changing the way you program things can have an impact on how conflicting transactions or read-write set errors can occur. So if you think of tokens and transferring assets, or like transferring money to each other, as a database person, we often think of accounts, right? Like every user will have an account which states how much money they have. This is, of course, problematic, because if you think of a largely distributed system where I'm trying to do different operations, because any single, I cannot in the same block have two transactions which change the state of the same account, right? Because they would, if you think of the permission space, they will invalidate, the first will invalidate the second when it gets to validation, right? Because the account amount changed by the time the second transaction is validated. So UTXO is the unspent transaction output that Bitcoin introduced. And the idea is that you think of not accounts, but you think of bills. So instead of saying how much money I have in my account, I track on the blockchain where each individual bill is. So, and to pay you money, or if I want to send money to someone, I basically take a bill I have, and then I cut it into two. I create now two half bills, and I send half of this bill to the person I'm paying, and I keep, for instance, the other half. So how this is done is by using public key cryptography. Basically, I own a bill if I own the money if I own the private key with which it was signed, and then I can pay to someone by basically cutting my my virtual bill, and then signing that half that I send to someone with their public key. So basically, this means that now we know that the person, or the entity who owns the private key for that piece of token will be able to spend it again. So you can think of now it's very easy to make transactions, because you don't have to know anything about the state of a user or the state of the other users. You can basically, by having a single token, you can make the payment. But now, for instance, reconstructing how much money you have in a specific account, or how much money a specific user has, becomes a costly operation, right? So it will be actually, you have to read all the state in the blockchain to figure out. And this is what, in principle, this gives you anonymity, because you can think of, there's nothing linking a person to the private keys, right? If I have this private key, if I don't tell anyone that I own these private keys, you don't know it's me. However, as you can imagine, whenever Bitcoin or other cryptocurrencies interface with the real world, you can work your way back, right? If I can somehow figure out that some value left the system, and I can link it to a human person, then I can work my way back and basically correlate which transactions happened at the same time. So as it actually happens, most of the Bitcoin transactions can be traced to this kind of accounts, which so we don't know who the account holder is, but we know that there's very likely a single entity who has been making payments. Does that make sense at a high level? Like maybe this is the point for me to stop and then open up for questions on anything that I spoke so far about.
I do not understand what you mean by cutting the bill in half.
Yeah, so you can
duplicating the bill.
Yeah, so let me see if I can maybe. So what you can think of is basically I can have something which says I have one token and there's a signature attached to this. So from this one token, I'm not sure if you can see maybe I should write bigger. So I say I have one token plus a signature. Now, if I have the private key for the signature, then from here I can create, for instance, 2 half tokens, which I sign again. They have their own signatures. So now the system, any public, this is public information, so I can verify for correctness that somebody made from one token 2 half tokens. I can see the value. This is in the plain text, but it is all down to the public private key pairs to decide who can actually make this computation. So in order to compute these 2 signatures, I have to have the secret. I have to have the secret information for this one, so I can create these 2. I cannot, unless if I don't have this secret information, I cannot produce the correct signatures here. So this is kind of how UTXO works, is by relying on the signatures and some secret keys, right? I can attest to the other members of the blockchain that I have this secret key here. I'm not disclosing the secret. I'm just showing that I could compute something that nobody else could have computed. The splitting is it plain text, so anybody can verify that from one blockchain I created 2 half blockchains. Sorry, from one Bitcoin or one Ether, I created 2 half Ethers. And then I can send this to someone by basically, you can think of the way I describe this signature somehow. If I encode something about Alice, then it will be Alice's secret that will enable you to further split this into parts. Now, of course, Alice doesn't exist. So in Bitcoin, there's no such thing as Alice. This will be some big sausage of a number, which will be a public key representation. So this is the whole idea of basically in Bitcoin. When you validate a transaction, what you check is that this splitting is correct, and then you check that somehow the signatures attached to these split parts are related to the signature in the original one. I'm a little bit oversimplifying things, but this is the underlying operation that is being done. What you also do is probably there's some amount, like 1% of this, which goes to you pay to the miner, or you pay in fees or something. You can imagine that every time you're doing an operation, you could actually pay in to an account. So you can think of like if you think of IBANs, like an IBAN where you can make a payment, a public key is like an IBAN. If I know a public key, I can send money there. Who that key belongs to, and how I can verify that public key belongs to the person I want to actually send money to, that's like outside of the Bitcoin problem. That is, that's where the identities and pseudo identities come into play. But you can think of this as basically IBANs. I can prove that the money I received here, I know I own that IBAN, and I can send it to 2 other IBANs, and they will be received. Did that clear it up?
Mm-hmm.
Okay. Any other questions?
Yeah, I was wondering, in the first part, you had the forking of the chain.
Yep.
I was wondering how this can happen, and whether it is possible to add another branch to a node quite a while in the past, whether the whole thing is a tree, or how the end of the valid blockchain is found, and this kind of questions.
Yeah. So this is a very good question. The answer is that this is all. Let me just find the slide so I can maybe draw on it. So when you have this this chain, as I said, by convention, I will hear in gossip, I will hear of different blocks. Like people will tell me, here's a block and this is where it fits. Now, I, as a member of the network, I will basically pick the blocks where I see that, okay, these fit together, so I can go and verify them like this, right? I can start from the oldest one and go to the newest one, and then every time you have you tell me this is block m+1, where this block is IDN, then I can check whether this connection is correct or not. Now, I could also get a block, as you said, which is not m+1, which is not the last one, but I could get a block at, if this is t, I could get it at t+1. And I could actually receive two, if I receive two blocks at t+1, both of them can be correct in the sense that both of them, if I hash this block, then the hash is inside. I can see that number, encoded in this block here and here, and the block itself contains correct transactions, and its hash matches the expectation. So I can have two valid blocks. So this is basically a tree. So it's a cycle. There's no, you cannot have cycles, but this can branch in any way. Now, by convention, I say that I pick the reality. I only work on the longest subchain. So I work on the one which has, assume there's no blocks here. So if this is longer than this subchain is longer than the other, my economic incentive is to try and add here. Because if I'm trying to propose a block here, this will never become the reality, right? So it's wasted work to try and add here. Now, if you think of the operation, like if I'm at now, I pause time and now I'm at block n. So this is my current. Everybody agrees that this is the last block. No forking has taken place. When you do the mining, basically what mining means is I propose here a bunch of blocks. I have tens or thousands of blocks here, and we all working in parallel on our cryptographic puzzles. And the first one to solve will basically make this link, and then we all throw away these blocks and we try to now add to this one here. Because that's kind of the economic incentive, is to always add to the block which has the highest chance of remaining valid. So, if you think of a double spending attack, what they call in blockchain can be that I say, I spend the token twice. So what does that mean? For instance, send you money. I send you money in this block here in the red. Let me here I send some money, and you give me the pizza for it or whatever it is. But then I maliciously create a fork, which now will become the new reality, which is here. And this new reality, I have not sent you money, right? Because this disappears. The state here is discarded. So this is a double spending attack where I could again pay you one more token here and get a second pizza. And from your perspective, I spend my money twice. And this is something that is a problem. So you probably don't want to accept this payment only after you had like 5 or 6 blocks already in the chain ahead of it, right? So on top of it, because at that point you are certain that, okay, well, you're not certain, but you are confident that no one will try to fork it back here. But from the data structure perspective, you could do this anywhere. So if you imagine like a partition problem, a network partition, this actually can happen, right? Imagine that for whatever reason, Europe and Asia get in a network partition. Then you could have Europe working on this side of the blockchain and Asia working on this side of the blockchain. And then when the partition resolves, I will start receive gossip messages from Asia, and I will figure out that actually this part here is longer than my chain, and I have to discard everything that we worked on here. So that's why, of course, in practice, these things, as I said, even in Bitcoin, I think the underlying economic incentive for everyone is not to try to do this, because the things that you can lose are disproportionately larger than the benefits you can get. But that is not to say that people couldn't try, or that doesn't mean that the system is safe. It's just that so far nothing terrible has happened. But it's a probabilistic data structure in that sense, or probabilistic finality, so that you never quite know. Of course,
Any
in a
other questions?
Sorry.
Sorry, go ahead.
No, I just wanted to say that in a permission space, like if you think of a database, of course, there, for instance, I think often what we would have in a distributed database, if you're thinking of like a log structure, right, that we add to, then the convention would be that because we're assuming non-malicious behavior, in many cases we just assume crash fault tolerance, then we always go with the block which was proposed earliest, right? So if we have two blocks being proposed at the same height, as they call it, or at the same index, I would just pick the one that was first put in there, right? I will write off the other one to some kind of conflict and just discard it. So, you know, in I think these problems appear more in this permissionless public space where I really have no control and no way of telling. There is no ground truth in the end, right? It's all probability.
Okay. Yeah, maybe a question from me is what is the pros and cons of using permission blockchain in, for example, in companies? What is the benefit and like disadvantage of it?
So I think okay.
Beside the trust, right?
Yeah. So I think if you're thinking of within a single company, so all the nodes, all the parts of the blockchain are under the same organization. You know, conceptually speaking, there's really no need to use a blockchain because what the blockchain protects against, or what it does, it distributes trust. So if you are basically running within the same organization, perhaps a distributed database would be just as good to you. Now, there's a small asterisk to that, in that, you know, there's some models like failure models where, you know, for Byzantine faults where you say, even though we're inside the same organization, we care about not only crash faults, but maybe, you know, some nodes being hacked or doing malicious things. Then, you know, you might be safer with blockchain simply because they have adopted BFT from the beginning, right? So I think most of the databases we know and use don't adopt the BFT consensus, right? So, you know, 2 or 3 phase commit is CFT, is crash fault tolerant. So it doesn't really help with actively malicious nodes, right? So I guess the point is that you could use permission blockchains, but I wouldn't say because it's the best choice, but simply maybe it brings some technologies, you know, it somehow this exists in the blockchain space and doesn't exist in the database space. But I think for the use case that you're describing, I'm really just inviting every database researcher to just add, you know, BFT. Let's bring BFT to the, you know, make it practical and like good open source implementations that we can run like distributed databases with BFT BFT assumptions underneath, and then you don't need all this machinery of a permission blockchain if you're inside the same organization.
Okay. Okay, thank you very much. So I think we can end the tutorial now. If you want to ask questions.
I'll please feel free to email me with any questions, or I'll try to be online a little bit on this on the Q&A part of the website. I still have to find it, but yeah, I'm happy to follow up with anyone on any topic related to this.
Thank you. Bye bye.
Okay, yeah, thank you very much. Bye bye.
Bye bye.